Okay, so welcome everyone. Welcome back from break. As we were just talking about a minute ago, it goes too fast and is never long enough. And today we're going to shift gears in a way, although this really is a combination of a couple of things, as we'll see. The big part of today's lecture is going to focus on the second half of acid-base chemistry, although in this case it's going to be focusing on more the Lewis side of it and not really so much on the Bronsted-Lowry. And then we'll see the second part of the experiment this week will actually tie together some of the reaction classes that we've seen so far. So I just wanted to quickly, the second part of the experiment is to make a compound called malachite, which is a copper compound that actually is a naturally occurring pigment. It's a copper ore, and it's quite prevalent in art history. So this is just two examples to show sort of the spectrum of use, both in Western art. Here, this Perugino's an Italian painting from the 15th century, and this Korean screen is actually a Japanese painting from the second half of the 17th century. So it's found naturally around the globe, and it's sort of a greenish blue pigment, depending on where it's found and how it's ground up. But we'll talk more about that later on in the class. All right, so what we're going to focus on today are transition metals. So I've mentioned those previously, but today we're going to dig a lot deeper into what they are. And there are three questions here which, themselves are quite simple questions, but their answers are rather complicated, as we'll see. So first, what exactly is a transition metal? That's the easiest of the three. How do they behave? Which is rather complicated because it actually is an entire field of chemistry that we call inorganic chemistry, or I should say a subfield of inorganic chemistry, since inorganic chemistry tends to look at metal chemistry, and transition metals only make up a part of that. And then something we'll also get into is where exactly the color comes from, because that, as we'll see in a moment, is one of the properties of transition metals, that they tend to have a color to them when in solution. All right, so we'll start with the first one, and that's what is a transition metal. And I just abbreviated that capital T, capital N, for sake of efficiency as we go through the next couple of slides. So in many cases, transition metals are called D-block metals or D-block elements, but this is not actually very precise because the definition, so there is something called IUPAC, which is the International Union of Pure and Applied Chemists. It's something you may have heard of when you learned about chemical nomenclature. We now use the IUPAC system in terms of consistency across chemistry. And the IUPAC definition is the following, and it's a transition metal is an element whose atom either has an incomplete D subshell or can give rise to a cation with an incomplete D subshell. Right, so in this case, we can have a transition metal, a metallic atom that is incomplete D subshell, or we can have a cation that's incomplete. Now, the importance of this is that the last family of the D block, and I have a periodic table on the next slide to just show this visually, the last family, which is group 10 of the series, is zinc, cadmium, and mercury. And it turns out, again, at the time when D block metals were thought to be transition metals, there was less known about the physical world. But at this point, we know that for these three elements, they all have D10 configurations, whether a metal or even as a cation, they have a complete D subshell. And it turns out that their valence electrons, when they do form cations, are from s orbitals. And that has to deal with the fact that having a D10 configuration stabilizes that whole set of orbitals relative to the s orbitals that are similar in energy. So here we have this one this periodic table, which color codes, and in this case here, we can see that the first 9 families of the D block are in this sort of Columbia blue color, because they're all considered the transition metals. And at this point, this periodic table is quite out of date because we have more than 110 elements now, although the ones at the bottom aren't super relevant to what we talk about since they're not really very stable. But the important thing is that from zinc, cadmium, and mercury, their family is more color-coded with the P group metals, right? So in terms of the organization, we have S metals, we have transition metals, and then we have P metals. And again, their behavior is going to be different depending on what we're looking at, and that's a big result of the electrons and the general electronics of the metals. All right, now, in terms of why we sort of distinguish transition metals to the main group metals, is in large part because of their chemistry, which is varied and very interesting. But transition metals are all going to have some basic characteristics, and these are not all exclusive to transition metals, but they are common to the transition metals themselves. Now, an important aspect is that they exhibit variable oxidation states, right? If we think back to experiment 3, when I introduced the oxidation state rules, there was a rule for group 1, which was alkalis are always +1, alkaline earth metals are always +2. The D block and the P block metals didn't really have a rule, although the P block metals, for the most part, have a pretty standard oxidation state. Some of those metals have maybe 2, some maybe 3, but they don't have very variable oxidation states relative to the transition metals. Now, by definition, they have to either have or form partially filled D subshells, right? In order to be a transition metal, by definition, one of those 2 things has to be satisfied. They can form compounds that are paramagnetic. Again, this is not exclusive to transition metals, but it is possible. And in large part, this is more common in transition metals because we're dealing with a lot more orbitals, right? In this case, we have 10 d orbitals to work with. And depending on the circumstance, meaning the molecule or compound we're looking at, there can be a varying degree of electrons. Now, as we'll see, in general, they're also going to form colored compounds or ions. And we'll see in a bunch of slides what the reasoning for that is. There is a chemical reason why these metals, when they are in compounds, tend to have a color to them. Now, another big aspect here, and this is a follow-up as well as a much broader and more in-depth discussion, is that they form compounds that consist of something known as a complex ion. Now, I had introduced the complex ion, not in those terms, a couple of weeks ago when we looked at spectroscopy, because I talked about the solvation shell when we put a salt into water, right? We had a salt, we dissolved it in water, and we ended up with aqueous ions if the salt dissolved, right? So that solvation shell, in certain contexts, we call a complex ion. Now, in that same experiment, we also saw that we were able to substitute, thinking back to spectroscopy, we started with aqueous iron 3, and then we added thiocyanate solution, and that gave us that orange-colored solution, right? So we sort of went from a colorless solution to that orange solution. And what was happening there is substitution of the ion. So in this case, we had water around the iron. We now substituted a water with thiocyanate. So it turns out now, sort of the continuation of that story, those are complex ions. And as we'll see, that substitution of a water for the SCN minus is something called ligand substitution, which we're going to get into in the next few slides. All right, now lastly, as a result of the first characteristic, meaning variable oxidation states, they do tend to have catalytic properties. And that's something we'll come back and talk a little bit about in experiment 8. because catalysis has to deal with rates of reaction. So when we get to chemical kinetics, we'll look at that. Now, just to give you a general sense, this is not something you need to worry about remembering. This is mainly just to give you some information about the possibilities for oxidation states. So this is the 3D, 4D, and 5D metals. And you can see here that some have vary more than others. But one thing just to point out, so again, for zinc, cadmium, and mercury, you can see that basically zinc and cadmium are only ever +2. That's because the ion forms by losing s electrons. And mercury can be +1 or +2, and again, that's coming from s electrons. Now, for those metals, for example, silver or copper, those also are either +1, +2 oxidation states, but it turns out those oxidation states are coming through the loss of d electrons, again, because of the definition we went through. All right, now just to there's a question. So the difference between the red and white circles has to deal with basically relative existence. So the red ones are the more common oxidation states. The white ones are, either the lesser available oxidation state, or in some cases it might just be ones that are only found during a reaction. So that, for example, iron here in the +6 oxidation state may not actually exist in a stable compound, but we can actually obtain that iron 6 oxidation state in some sort of reaction. So the difference between the red and white is about basically the likelihood of finding it sort of in stable compounds. All right, now just to go back, this is a substance, a compound that I had talked about earlier, and I just quickly introduced it when we looked at redox chemistry, but this is hemoglobin. And now we're going to dig a little bit more deeply into this, because now we're going to look at the actual heme, which is what contains the iron in hemoglobin. Right, so you can see here hemoglobin, and this is just a visual schematic, is these 4 coils. So there's these beta chains and alpha chains of the metalloprotein, but each of them is going to contain one of these iron hemes. So I have here in 2 different angles. So this is looking down, right? So as you can see in the depiction, the heme is represented as basically a pink sheet, and then the red dot in the center is the iron ion, right? So here, this is looking down, and you're looking onto the plane of the heme. And this is from a side view, right? So again, we can see this big circular structure is the heme. And then around the heme is also a few other things, right? And in the center of that is the iron, right? Now, importantly, this, again, right, this is basically a shell of things around the metal center. This is an iron 2 ion, but it's surrounded by 6 things. Now, we'll get into this a little bit more in the coming slides, but one thing that I need to point out here is that in transition metal chemistry, when we are looking at complexes, as opposed to, say, if we just had iron nitrate salt, right, that's a relatively simple compound, because in the salt, it would just be iron and nitrates, and depending on the oxidation state, the relative ratios to satisfy that. Right, in this case, we are now looking at a complex ion, because here we have a metal, in particular iron, but it's surrounded by a lot of other things. Now, a key distinction here that is probably new to most people is the fact that here we have metals and nonmetals combining in a not ionic type way. So in transition metal chemistry, one of the reasons why it can be quite complicated is because you have the gamut of bonding. In certain cases, there can be ionic type bonding. In certain cases, there can be regular covalent bonding. And in many cases, as we'll see, you can have that coordinate covalent bonding, right? Again, thinking back, since this is the second half of acid-base, right? The characteristic of a Lewis acid-base reaction is that donation of a lone pair to form a coordinate covalent bond, right? So here, a big hurdle to sort of get over is to realize that these are not just all sort of simple ionic bonds. The bonding, which we will simplify greatly, is rather complex and varied depending on the circumstance. All right, now, again, that being said, I want to go through and define a couple of terms which are important for this discussion, and then we'll come back and look at those terms through the lens of that iron heme, through that metal center in hemoglobin. All right, so the first is a coordination complex or complex ion if it's charged. And that just depends on the circumstance in terms of what the charge is. It can be neutral, it can be positive, it can be negative. And that basically, in all of those cases, is some species where a central metal ion is coordinated to what we call a ligand. Now, in terms of the terminology, coordinated is generally the term we use in this area of chemistry to mean bonded, right? We use coordination as a more general term because the bonding can be a little bit varied, as I said. So if you see the term coordinated, you can just think that basically means that something's bonded to something else. In this case, these ligands are bonded to the metal center, right? And basically, everything's going to be focused around that metal center and what's actually around it. So a ligand is any molecule or ion, and this definition is somewhat circular, but it is what it is. It's a molecule or ion that is directly bonded to a metal ion in a complex. And the term ligand comes from the Greek word ligare, which means to bind. Right, so again, we have another term, coordinated, bound, bonded. All of these terms effectively mean the same thing here. Now, the interesting thing, although the complicated part, is that ligands can vary in what we call denticity. And denticity basically means the number of atoms directly coordinated to the metal. Right, so denticity has to deal with, in a way, right, the teeth that the ligand has to the metal center, right? So if the ligand only donates one atom, then it would be a monodentate. So that's mono again, like monoprotic, one acidic proton. Monodentate would be one binding site to the metal center. Now, if it's two, it's bidentate, tridentate, so on and so forth. We're only going to look at, in our experiment, monodentate and bidentate ligands, but you basically can go anywhere from 1 to 6. So you can have a monodentate up to a hexadentate type ligand, depending on what it is. All right, now importantly, and related to that, is something called coordination number. And in a way, coordination number is similar to steric number that we have seen with Lewis structures. And in this case, that coordination number is the number of ligating atoms, right? If your ligands are all monodentate, then you have 6 ligands and your coordination number is 6. But if some of your ligands are multidentate, then your coordination number and total number of ligands is not the same. And we're going to see hemoglobin is an example of that, which we'll get into on the next slide. Now, there's another term which is called coordination sphere. And the coordination sphere is not super relevant to what we're going to see because the complexes we work with are relatively simple. But in more complicated complexes, like hemoglobin, for instance, the coordination sphere is basically just the metal center and the elements around the metal center, right? So as we'll see again with hemoglobin, that big planar structure is all one big ligand, but really what's being donated are nitrogen atoms, right? So the coordination sphere is nitrogens, but the ligand itself is that big complicated structure, right? So it's a subtle difference and much more relevant when you're looking at big complicated compounds with, rather complex ligands that aren't simple molecules or ions. All right, so now we'll apply these definitions to this example. Oh, so there's a question. So coordination complex is the entire species, right? So if we're looking at some complex ion, that's the entire coordination complex. The coordination sphere is exclusively looking at the metal center and the atoms immediately surrounding it, right? So basically, you're looking at the atom donated and sort of ignoring the rest of the ligand. Again, for our purposes, it's not super relevant to what we're going to see, but nonetheless, it is a term that you may come across. All right, so now again, and this is a good example of this. So if we look around our iron, we can see there's a question. So denticity is referring to the number of atoms the ligand can donate. So if it's a monodentate ligand, its denticity is 1. If it's a bidentate ligand, its denticity is 2. Now, how that relates to coordination number is that denticity adds up to give you the coordination number. So the total denticity is the coordination number around the metal. All right, so if we look at the iron in hemoglobin, and again, this is the iron within the iron heme, right? Around the metal center, right? So if we were looking at the coordination sphere, right, we would say the iron's in the middle. There are 4 nitrogens around it. Then we have an oxygen above. So the dashed line is used in this case to give you some sense of geometry. So you have a plane and then something on top and something underneath, right? Underneath is this structure, which is something called histidine. It's a residue, an amino acid. So what you have here is, right, basically 6 things around the iron. There's a question. So the denticity of the ligand, I mean, it depends a little bit on the circumstance, but in general, it has to deal with the ability of the ligand to donate electron density to the metal. So for our purposes, it's going to be pretty clear based on the ligands we work with if they're monodentate or bidentate. In more complicated circumstances, it requires a little bit of investigation to know what kind of denticity the ligand may have.
Professor, can I ask a question about that? I know that I'm just TAing, but is it okay if I ask a question about this?
Sure.
So if we're looking at this complex right here, and we were trying to determine the denticity, I mean, would it be closer to a hexadentate because you have like those 6 different ligand sites, or would it be like monodentate because there's only 1 nitrogen in there? When you remove the ligands, like when you take the ligand apart from the metal center, you're going to have a single negative cation next to that. Or am I thinking about that?
So I'm going to get into that next. So hopefully that will help clarify. Okay. So I guess so in terms of, to start with that, around the iron, right, there are 6 elements, right? So there are 4 nitrogens in the plane, an oxygen above and a nitrogen below, right? So in terms of coordination number, that would be 6, right? Because there are 6 elements surrounding iron. Now, in terms of the ligands, that's where we need to now look a little bit at what is actually binding or coordinating to the iron, right? So the ligands that are at play here are the porphyrin. So the porphyrin is this big planar structure in the middle, right? So that is that circular sort of what we call a heterocycle, right? Now, in that case, all of those nitrogens in the plane are being donated from that porphyrin, right? So if one ligand, because this is one big molecule, is donating 4 atoms, then that means it is tetradentate, right? So the denticity is really referring to the ligand, not the metal, right? The total things donated is coordination number. What each ligand donates is denticity. So here the porphyrin is tetradentate. It's donating 4 nitrogens. Now, oxygen, right, that's a much simpler molecule because it's just 2 atoms. And in that case, that would be monodentate because geometrically it can only donate a lone pair from one side. And then the histidine underneath is the same thing. That histidine is also monodentate, right? And that's evidenced by the way it's connected because there's just the nitrogen being donated and here the oxygen being donated, right? So as I said, the coordination number is 6, but you only have 3 ligands present.
Sorry, Professor, could you just walk us through one more time how we know that the nitrogen is really only one ligand that is tetradentate as opposed to 4 that are monodentate?
Well, right, if you look, right, this whole this is all connected, right? So for a ligand to be monodentate, it needs to be a standalone entity. And in this case, and again, this example I gave because it's exceedingly relevant to, a biological example. The ligands we're going to work with are not this complicated, but this cyclical structure is entirely connected, right? The nitrogens aren't being donated separately. They're all part of this one big macro cycle, which was why that would be a tetradentate ligand. There's a question. So the octet rule does not apply here anymore, right? The octet rule is something, yes, it was our mantra in the Lewis structure activity, but that was the mantra then because we only looked at main group elements. The difference when we go to the D block is that we no longer have the octet rule. We have something called the 18 electron rule. So there still is an octet rule of sorts, but it's not 8, it's actually 18. And that's because the electrons we can potentially be working with would be S, P, and D, which when you add those up, you have 2 plus 6 plus 10. So the octet rule in transition metal chemistry is not really the one that we're worried about. Now, within the compounds, right? So in histidine, which is an organic molecule, in the porphyrin, which is an organic molecule, the octet rule applies because those are all main group elements. But in the complex around the iron, the octet rule is not what we're worried about. Yes, so again, the nitrogens are all part of one ligand, which is this planar molecule in the middle, and that is giving us 4 nitrogens to the metal center. So it's one ligand that donates 4 atoms, which would make it tetradentate.
So, Professor, just to clarify, so porphyrin is the entire structure attaching to iron except for O2 and histidine.
Correct.
Okay.
Yep. Yeah, so this whole big molecule in the middle is all connected, and that is simply one ligand. It's just donating 4 nitrogens.
So Professor, in this case, as long as they are connected, like there's one bond, and they will consider as one ligand.
Well, so if the ligand is only donating 1 atom, right? So like O2 is only donating 1 oxygen, then that's monodentate, right? Same goes histidine is only donating a nitrogen, so it's 1 atom. And then in the center, we have one ligand donating 4 atoms.
We consider this as one ligand because they are all connected together.
The porphyrin is, yes.
So, for example, if in this case, if there in this the big molecule, the plain molecule, what if there's a carbon is connected to the central ion? What will change in this case?
Well, if this was donating another element, so if this was some other element that wasn't, although carbon isn't really a very good ligand because it doesn't have lone pairs, but if this was a different element, say these were oxygens, it doesn't change anything because that still is four atoms being donated.
Oh, so we consider most time we use the atoms with lone pair as ligand.
I mean, yes. So in many cases, the lone pair is what's donated. As I said, the bonding is complicated, but in general, we are going to view a lone pair being donated from a ligand.
Oh, thank you.
Yeah, sure.
I'm sorry, Professor, I still have a quick question.
Yeah.
So in this case, we consider which part as Lewis base, which part as Lewis acid, as they're donating and accepting electrons.
So I will get to that in a moment.
Okay, thank you.
Yeah, sure. There's a question. Yeah, the dashed line, as I said, is just representing, that's trying to give some geometry. So all of the solid lines are in the plane, and these dashed lines are above and below the plane. So it's simply representing geometry. There's a question. So, I mean, at this point, I haven't talked specifically about what the bonding is. A double bond would not really, I mean, again, most of this bonding deals with lone pairs. So a double bond isn't really something that we're going to see that donates. Yeah, it's mainly going to be, again, lone pairs. All right. Now, in terms of the question that was just asked, again, since I said this was a continuation of acid-base chemistry, and thinking about what a ligand can do relative to the transition metal, we can see that the metal is electron deficient, right? In general, there's going to be, well, there has to be vacancies in the d orbitals to be a transition metal, and that deficiency is going to be made up in these complexes. So in general, the metal is considered a Lewis acid because it can accept more electrons. Therefore, in general, the ligands would be viewed as a Lewis base. Now, again, this is a generalization, not a hard and fast rule, but for our purposes and what we are going to see in our experiment, we can consider the metal a Lewis acid and the ligands Lewis bases. And again, they are forming coordinate covalent bonds when they form this complex ion. And that's due in large part because of that 18 electron rule. So there's a question. The complex is just a complex. The way in which this complex forms is a Lewis acid base type reaction. But the complex itself in this stage is not an acid or a base. It's simply a complex ion. And in this case, the structure of hemoglobin, the structure of the iron in the heme is what allows the oxygen to be brought into the body, right? This O2 here is what's going to come and go as needed as we breathe in oxygen. So the complex itself isn't an acid or a base in this form. All right, so now we need to take a look at the actual electronic structure of these complexes. Now, that is all going to be governed by the d orbitals. Now, the d orbitals are degenerate, meaning they are of equal energy in an isolated transition metal atom or a transition metal ion. So if we just have a transition metal atom sort of, in a vacuum, right, which is sort of a hypothetical scenario, the orbitals are equal in energy, right? And for the 3d orbitals, this is what they look like. There's a question, so the formation of the complex is an acid-base reaction. Yes, that is correct. So forming a complex ion is the acid-base type reaction. Now, in terms of the orbitals, and again, these are all going to have the same shape, whether it's 3D, 4D, or 5D. The only thing that changes is the size and the number of nodes. But the one key distinction that's going to be important is that two of these orbitals lie on the axis set as defined, right? We have here an XYZ coordinate plane. And what we're going to have is two orbitals along the axes and three in between the axes, right? dz squared is along the z, dx squared minus y squared is along the x and y, and then xy, xz, and yz all are in between those particular planes that, or the particular axes that are in the subscript. Right now, one way to remember this is the fact that a subscript that has a square are on axis, and a subscript without a square are not, right? So z squared, x squared minus y squared on axis, xy, xz, yz in between the axis. This is going to be important because as we start thinking about making a complex ion, this geometry is going to be a critical detail. All right, now the model, and again, keyword model, that we are going to use to think about the structure of these electronically is something called crystal field theory. Now, this is a somewhat older model. At this point, MO theory is the best one, as we've talked about previously. But the result of crystal field theory is actually quite comparable to MO theory. It's just that the reasons for it are not correct, as opposed to MO theory, which doesn't make some of the assumptions that are made in crystal field theory. Now, crystal field theory all relies on the idea that atomic orbitals are perturbed due to electrostatic interactions with the ligands, right? So what we have here is, again, this hypothetical complex. We have a metal center at the origin, and around it we are bringing in 6 ligands, right? Now, importantly, we have to define a geometry because this derivation is going to depend on the shape of the complex, right? That's another layer that we have to be cognizant of. So in this picture, it is a coordination number 6. Now, the underlying assumption here is that the ligand is a negative point charge, right? And this is an assumption that we now know to be incorrect. But again, it's sort of a simple assumption that we could use in the model, right? So it assumes that the ligand is a negative point charge, which means that it's a negative charge with basically no volume, right? And as we bring a negative charge towards the metal center, that negative charge is going to interact with electrons, right? The d orbitals will be around the metal center, and while they may have vacancies, they're not completely empty of electrons, right? Transition metals have some d orbital electrons. They just have room for more. So that interaction between the electron in the d orbital and the negative ligand is the electrostatic interaction, right? And in this case, a negative-negative interaction is disfavorable, right? That's a disturbance or a perturbation because that's a non-favorable interaction. Now, the part that we need to account for the geometry is the fact that if we are bringing those negative charges along the x, y, and z axis, right? That's how we're orienting the complex. If I just go back here, right? That's why I have these 6 yellow circles coming in along x, y, and z, because I'm basically building, hypothetically, an octahedral complex, meaning 6, coordination number of 6. So if I think now about what happens along those axes, it's going to be different for 2 of those orbitals. Because along the x squared minus y squared orbital and the dz squared orbital, I am going to have head-to-head interaction, right? Because the lobe of the z squared can interact with the 2 charges. And same thing on the x squared minus y squared, the lobes will interact with the 4 charges on the xy plane coming in. Right now, in terms of the other 3 orbitals, those are not going to have that head-to-head collision because of their orientation in between the axes. Right, so that means there's less perturbation for those 3 and more perturbation for these 2. Now, what that means is that the orbitals are no longer going to be equivalent in energy because 2 of them are going to be destabilized more than the other 3. Now, just to show some geometry here, there's, and we're not going to watch this whole clip because this goes into different geometries. We're only focusing on octahedral. And there's just about a minute of this video that's going to show us a little bit about that geometry to help visualize this. Now, let me know, I'll start this and let me know if you can hear the audio.
Crystal field theory explains most of the properties of complex ion bonding. Ligand field theory is actually MO theory applied to complex ions and is only briefly considered in these tutorials. The idea of crystal field theory is that the ligands approach the central atom and create a local crystal-type field, and this affects the d orbitals of the central atom. Transition metal chemistry is dominated by the d electrons that can occupy the 5d orbitals. Here is shown the 5d orbitals of the free central atom. Also, the 5d orbitals in the tetrahedral field and the 5d orbitals in an octahedral field. For a free transition metal, in the absence of any crystal field, the 5d orbitals are degenerate, which means that they all have the same energy. In an octahedral field, 6 ligands approach, 2 along the plus and minus z-axis, 2 along the plus and minus x-axis, and 2 along the plus and minus y-axis. When a ligand encounters a lobe of the central atom's d orbitals, it raises the energy. Hence, the dz squared and the dx squared minus y squared orbitals, which lie along the x, y, and z axes, are raised in energies, whereas the dxy, dyz, and dxz are out of the way of the ligands and are of lower energy. In a tetrahedral...
All right, so we're going to stop there because we're not going to really worry about tetrahedral geometry. There's a question. So octahedral geometry is coordination number 6. So don't let the octa part is not referring to the coordination number. Octahedral, for that description, has to deal with the fact that the 3-dimensional shape of that has 8 sides if we look at it as a geometric shape. right? So octahedral is coordination number 6. It's not coordination number 8. It's unfortunately the name of that comes from the geometric shape, not the orientation around the metal. All right, now, so before we move on from here to just finish this topic, are there other questions or clarifications so far?
Professor, in this case, the crystal field is important.
Oh, I'm sorry, say that again.
Why in this case the crystal field is important for us to know?
Well, this is just the particular model. So I haven't really gotten to the punchline of sorts yet. So the importance of a model to explain the bonding here is because we're going to see what happens to the d orbitals on the next slide, right? So the crystal field theory, which again, at this point, the full MO theory of it is more accurate, but the result of them is the same, and that is that we end up with a split, right? So as I said, we start with degenerate orbitals, and they also did a little bit of this in the video, right? All of the orbitals are at the same level. This is just a general energy scale. And after we form the complex, in this case, an octahedral one, we end up with orbitals at 2 different energies, right? So the importance of crystal field theory is that this shows us where this energy split comes from. And the importance, so really the whole gist of going through this is because this energy gap is where the color comes from in these complexes, right? One of the properties I said is that transition metal complexes have a color to them, right? But if we think back to spectroscopy, that color has to be due to absorbance in the visible region of the spectrum, right? So absorbance has to be an electron absorbs energy and moves from one energy level to another. And in this case, crystal field theory shows us that energy split, right? So this here is what we call the del O, which I'll get into it a little bit more on the next slide. But the importance of this model is this 2/3 split. There's a question. So so crystal field theory itself, the model is flawed because the assumptions that I explained, meaning, point charges for ligands, and electrostatic perturbations are not entirely true, right? There are many ligands that are neutral, and ligands for sure have volume. They are not just a negative charge. Additionally, again, the bonding is not so simple as just electrostatic perturbation. It's just that the result of crystal field theory gives us this energy split. And this turns out is the same split we get in MO theory. But trying to go through and explain how the atomic orbitals mix to get to the split is a lot more complicated and, really beyond what we're looking at here. Now, importantly, and this is why I said we only viewed octahedral, that depending on the geometry around the metal, the split is going to be different because the orbitals will interact differently with the ligand orbitals. So that's something to just be cognizant of. This 2/3 split is only in an octahedral geometry, which would be coordination number 6. All right, now the energy split that in this case, since it's in crystal field model, we call it the crystal field splitting energy, right? That's the split between the orbitals, which we for short call del O, right? So that's short for delta energy in an octahedral geometry, right? So if we were, say, tetrahedral, we'd have a del T, the delta energy for the tetrahedral geometry, or a square planar geometry, depending on what it is. All right, now, again, in terms of that energy split, if we think about we've seen copper solution before, right? And we know that it was a blue solution. And I said the lambda max was around 612, which is an orange absorbance, right? Well, what's actually absorbing that energy? Well, it turns out that an electron in a lower energy d orbital is going to gain that energy and shift upwards, right? So the importance of that split is that the energy gap between the orbitals is somewhere in the visible region of the spectrum, right? Because, 610 nanometers corresponds to an energy, right? And it turns out that the color in these compounds is often a result of an electron, a d orbital electron, being promoted from a lower energy to a higher energy state. Now, we're not going to get into there's obviously a lot more at play here because there can also be emission, but, we're going to focus on the absorbance part, right? So the color of these complexes is coming through absorption of visible light in the d electrons. All right. Oh, there's a question. So these arrows here represent the electrons. So in copper 2+, there happen to be 9 electrons that we're working with. So the up and down arrows aren't overly important. The key takeaway is that one of them is being shifted from a lower energy to a higher energy orbital, right? We're not going to really worry about counting electrons anymore. That's not something we're going to really worry about because it's, again, it's quite complicated here in this area of chemistry. There's a question. So, with respect to hemoglobin, that's a little bit more complicated because that is a much bigger complex, right? In this case, this is just aqueous copper ion. In hemoglobin, that's a much bigger complex, and it's also in a very different environment because it's in us, right? And yes, we're water-based, but there's a lot of other stuff around, so it's not just a simple solution of water. And in terms of what the actual changes on the heme are is also complicated because the actual uptake of oxygen is a redox process. So when the O2 binds, it goes through a whole series of steps where the oxidation state of iron changes, and the oxygen is also carried along into other molecules. So that that's not quite as simple as this basic model that we're looking at, because of a very different context. All right, now in terms of, right, as I said, we have that split based on the model, right? But the model just assumed a negative charge for the ligand, right? But at this point, we know that there are lots of different ligands. They're not all negatively charged. Some may be monodentate, some may be bidentate, and so on. And it turns out that depending on the ligand, it's going to have different ability to split those orbitals, right? So the tool that we use for that is something called the spectrochemical series. And the spectrochemical series is, similar to other tools that we've seen. It's a generalization that ranks the strength of a ligand. Now, in this case, the strength of a ligand has to deal with the ability to split the orbitals, meaning a weaker ligand splits less, a stronger ligand splits more, right? That's the general trend. Now, why some ligands are weak and why some are strong, it depends very much on the orbitals at play, which, is in large part an entire graduate class, if you're interested in that. But there are, various factors that determine the strength. Now, the nice thing, though, is, even without necessarily understanding the full reasoning, the spectrochemical series gives that to us. right? And we can see here, starting from here, and unfortunately it's on 2 lines unless I make it super tiny and impossible to read, but basically we're starting here with iodide at the bottom and CO, carbon monoxide, at the top. Now, one thing I will say is, if we notice just visually, right, the halogens are at the bottom, right? So the spectrochemical series is not about electronegativity, right? In many cases, that sort of is a factor that we worry about, but it is not the determining factor here, right? Because the halogens are all at the bottom end. In the middle are the oxygen donors, right? So we have hydroxide ion, oxalate, which we've seen. We used that to precipitate out calcium a couple of weeks ago. But in this case, it can actually be a ligand. And then we have water. Then we have nitrogen and phosphorus donors, right? So ammonia. Ethylene diamine, we shorthanded EN, and I'll have the structure of that in a slide or two. Here, this is what we call a phosphine. So in inorganic chemistry, phosphorus donors can be common. And this one happens to have, this is triphenylphosphine. So there's three benzene rings around that phosphorus. And this basically looks the same as ammonia, right? Nitrogen and phosphorus are right under each other on the periodic table. Nitrogen with 3 things has a lone pair. Phosphorus with 3 things has a lone pair. Now, at the top are cyanide and carbon monoxide, right? And in this case, these happen to be carbon-based compounds. Now, it's not because of carbon that makes them so strong. It's, again, because of a particular ability of their ligand, of their orbitals, to create very strong bonds, right? And if we think about this, right, cyanide ion and carbon monoxide are highly poisonous to us, right? And that's in large part because they are very strong ligands, right? And for example, and this is, this would be true for any kind of metal, because they are such good ligands, if we think about hemoglobin, if one of those ions, which again, they're pretty much a similar shape to O2, right? O2 is a linear molecule, so are these, right? But if cyanide ion or carbon monoxide binds to hemoglobin, it's so strong a bond that it can't fall off, which means that the hemoglobin is basically then dead, right? The hemoglobin can no longer uptake oxygen, right? So again, that's one of a few examples why these 2 species are so toxic to us, because of their bond strength. Yeah, there's a question. So thiocyanate happens to be ambidentate, right? So in this case, sulfur and nitrogen in this molecule both have a lone pair, and in certain circumstances, it binds through sulfur. In certain circumstances, it binds through nitrogen. Now, which situation it prefers, it all depends on the metal. Some metals prefer sulfur, some metals prefer nitrogen. And again, you can see here, as a sulfur donor, it's on the weak side. As a nitrogen donor, it's sort of in the middle, right? So that is one ligand that can bind through either direction, through either atom. There's a question about absorbance. So I'm actually going to go through an example in a minute to try and help show how all of this works together and what it means in terms of visible light. All right, so here we're going to focus on, and these are actually experiments that you'll see in the module, but we're going to focus on the left-hand side of this diagram, right? So here's the color wheel back from experiment 4. And we're going to look at 3 different, we're going to look at a solution, and then we're going to add in different ligands, right? So at the top, I know it's a little bit hard to see, but what we are starting with is aqueous nickel 2. This would be nickel nitrate dissolved in water, right? So the complex ion, right, is the solvation shell. It would be the nickel with the 6 water molecules, 2+ charge. Now, what I've done here, because the oxygen is what's donating the electron density, I've started the ligand with that, right? H2O and OH2 are the exact same thing. I just rearranged the letters, right? Now, you don't need to worry about this formalism for the report. I'm just showing it to you here so you see what that looks like, right? So in this case, nickel H2O6 or OH26 are exactly the same thing. Right, now if we think about this, if the solution is pretty much green, right, we say, all right, well, if we see a green solution, then based on the color wheel, we would expect a red lambda max, right? And in that case, that is the longest visible wavelength because it's the lowest energy visible light, right? So now we have here, this is our just solvation shell. It has 6 waters around it. Now, if we add a ligand, in this case, I'm pouring in ammonia, and I can see here that the color has changed, right? I go from a green solution to a blue solution, right? Now, that's going to be the key observation in this experiment. A color change is indicative of ligand substitution, meaning that the initial ligand gets substituted by the new ligand. So I'm adding ammonia. Again, a little hard to see, but it says add NH3. And I see now that my solution went blue. So what I'm going to do is substitute my 6 waters for my 6 ammonias. Now, I'm going to give some guiding principles for how to come up with these subscripts in terms of coordination number. But for right now, we're aiming for 6. Right, so the most common coordination number in aqueous chemistry of transition metals is 6. Right, so we start with 6 waters. Ammonia is monodentate because it donates a lone pair from the nitrogen. So we substitute 6 waters for 6 ammonias. Now here again, if we think about the solution turned blue, right? So that means now we're here on the color wheel. Right? So if we see blue, that means we absorb orange. So now we went from initially a red absorbance to now an orange absorbance. Right? So that means that the energy absorbed is higher in frequency, right? It's higher energy. We go from red to orange. Right? And that's a result of the stronger ligand. We start with water, we add ammonia. Right? And if I just go back a second, ammonia is above water. Water's sort of in the middle. Ammonia is above it. It's a stronger ligand. Right? So, and now that's reflected if we look at it in a slightly quantitative way. We go from a red absorbance to an orange absorbance. Now we do one more experiment. We add ethylene diamine. So ethylene diamine is sort of related to ammonia, but it looks like this. And again, the shorthand for it is EN. And the difference here is that this is a bidentate ligand, right? We can see that there are 2 nitrogens in ethylene diamine. So therefore, it has the ability to donate both of them. Now, ethylene diamine is stronger yet than ammonia. So we add in our ethylene diamine, and now our solution went from blue to purple. So we say, okay, a purple solution now absorbs yellow light, right? And again, going from orange absorbance to yellow absorbance is higher in energy, right? Those d orbitals are being split more. Now, one last aspect of this, right? So far, all we have looked at is the splitting, right? I'm saying that the splitting of the d orbitals starts out in the red range, then it goes to orange, then it goes to yellow, right? So the split between those 2/3 orbitals is increasing. Now, the important other detail here, and we're not really going to get into too much of this because it's a little bit sort of hard without getting into all the MO stuff to go sort of get into it. But a stronger ligand, in addition to being able to split orbitals more, also makes stronger bonds, which lowers potential energy, right? If we go back, I have to go back a lot of slides, but in that energy scheme, right, I am simply showing the orbitals going up, right? Because that's a hypothetical derivation. But what can happen, and what does happen with stronger ligands, is even if those orbitals split more, I'm not explicitly saying, do they also move up or move down, right? So a stronger ligand is going to make a stronger complex, and that's going to lower the overall potential energy, right? So we have two different factors: the difference in energy between the orbitals, but also their relative position on the energy scale. So even though a stronger ligand has the ability to split orbitals more, it also is going to lower potential energy. And that part is a little bit harder to sort of quantify in a nice simple way, as these three colors sort of show. But in general, that's going to be the trend. Well, there's a question. So weaker ligands are going to split orbitals less, which means that the energy absorbed by the electron is weaker or longer wavelength, depending on how you want to think about it. It's not the ligand that's absorbing the energy, it's the split, and the transition metal electron is then absorbing higher or lower energy. Yes, split more means there's a greater difference between the orbitals, right? So smaller splitting is less del O. Higher splitting or larger splitting is greater del O, right? Because the energy is correlated and inversely proportional to wavelength.
Excuse me, Professor, could you explain again what makes a ligand like stronger? What's the factor to decide a ligand is stronger and the factor is weaker, or is just memorization?
Well, so as I said, so it's not memorization, because I give you it's just a matter of using the spectrochemical series, right? So the reason why the spectrochemical series is organized in the way it is not for one particular reason. Because weak ligands are weak for a particular reason and strong ligands are strong for a different reason. It's all about orbitals and the ability to overlap and make bonds. But again, the particular of that is not just one simple answer. But the spectrochemical series is a sort of simple tool we can use that ranks the ligands for us. So it's a matter of using the spectrochemical series to think about the strength of that ligand.
Thank you.
Sure. Yeah, so that is one way of putting it. So a stronger ligand forms a complex with lower potential energy, but larger splitting of the d orbitals. That is correct. So again, it's two different energy things. The potential energy overall is going down. The splitting of the d orbitals is going up. All right, whoops. All right, now one thing just to close out this example is the fact that since ethylene diamine is bidentate, we're still trying to get to coordination number 6, which means we only need 3 of them, right? A bidentate ligand gives 2 atoms apiece. So if we have 3 of them, that gets us to coordination number 6, because it's 3 ligands times 2 each, which would be 6. Now, again, in terms of the rules of this, I do have a slide, which I'm going to try to get to, although we're running quite late. Well, actually here, so we'll go right to this. So as I said, the experiment is 2 parts. The first part is from Barron, and that is going to look at a series of complex ions to get at the issue of ligand stability, and to also give you some sense of what these complexes look like visually and what impact the ligand has on the metal. Now, we're going to have general rules. One of the fun yet also complicated parts of transition metal chemistry is that most of the generalizations have more exceptions than items that hold to it. So I'm going to present a set of rules that we're going to follow as just guiding principles, with the big caveat that, this may not apply perfectly to every situation, right? These rules are particular to our experiment and how we're going to just sort of simplify this as much as possible with respect to our data. Now, this part is true. So the most typical coordination numbers are 4 and 6. Right, coordination number 6 is octahedral, as we've already seen, since that's what we used for the crystal field derivation. Coordination number 4, we have two options. One of them is tetrahedral. That is the more common of coordination number 4, but we also going to have square planar geometry. Right, now, importantly, these coordination numbers, we are only focusing on the ligands. Right, so the difference here between Vesper and coordination number of a complex is we are only considering bonding domains. We're not looking at lone pairs here. So this would be, 4 bonding domains, and it can either be tetrahedral or square planar. Right, square planar Vesper geometry comes about in a slightly different way, but that's where the context is important and a little bit different here. Now, for coordination number 4, that is preferred if the ligands are bulky, meaning that they're physically big, or as we'll see, electronically big, or in some multidentate ligands that are just sort of rigid, right? So if a ligand is kind of rigid, it may force a complex to be a certain geometry. Now, for the ligands we're going to work with, of which there will be 5 of them, 6 including water, chloride is the only ligand that prefers to be tetrahedral. And this, again, is a generalization because chloride is electronically bulky. Electronically bulky means that we have a lot of electron density around a very small ion, right? Chloride ion is quite tiny, and there's a lot of electrons around it. So as a result, when we are trying to put it around a small transition metal, putting 6 of them causes too much electron-electron repulsion between the ligands, right? And electron-electron repulsion is bad, right? So having 4 chlorides is more stable because it gives the ligands more room. So that being said, if you think a complex forms with chloride, then that would be a tetrahedral geometry. Now, one last little wrinkle / layer is the fact that if you look back at the spectrochemical series, chloride is actually a weak ligand. Now, that being said, a weak ligand does not mean that it's impossible to form a complex with it. But what it means is that it's not going to necessarily be very stable, and you may have to do something a little bit extra to make it happen. In this case, that key variable is concentration, right? So in our experiment, we are going to use HCl, right? That's a strong acid, which means that the concentration of the acid is basically the concentration of the chloride. And if you have a highly concentrated amount of ligand, you can force weaker ligands to occur in certain cases, right? Again, energetically, it doesn't necessarily want to form, but you can force it to form because of that concentration. So again, in part A, that's something to be aware of because that's where we're going to look at chloride specifically. Now, for the other parts, so parts B, C, and D, and we're going to be looking at 3 metals for everything. Copper, nickel, and cobalt all in the +2 oxidation state. Right? Generally speaking, we are going to aim for coordination number 6. So in parts B, C, and D, we're trying to get to coordination number 6. We're just going to make it easy. We're trying to have the same coordination number in all of those complexes. Again, the one exception is part A, because chloride's a little bit different and prefers tetrahedral. Right? So in terms of the general rules, part A would be coordination number 4. Parts B, C, D is coordination number 6. Now, again, as I said, that is purely a generalization, and many, many exceptions certainly exist, some even amongst the ones we're going to look at. But just to try and keep it, again, as simple as we possibly can, that's the generalization we're going to follow. Now, the last little caveat is with copper. So copper 2+ is a little bit different than the other two metals because of the amount of d electrons it has. And as a result of that, right, this is not something that necessarily we wave our hand and it happens. This is just the reality that we've discovered as more and more data has come about. So in copper 2 complexes, in many cases, the complex exists as a distorted octahedron. And this has to do with the fact that because of all the electrons on copper, it ends up distorting its own orbitals to lower its potential energy, right? The bottom line is, in chemistry, is always trying to lower energy. So with copper 2, it actually reorganizes itself to get to a lower point of energy to be more stable. Now, at this point, this is what we call the Jahn-Teller effect, right? Again, this isn't something that we make happen. It's just an effect that occurs as a result of the specifics of copper 2. Now, there are other metals that also fall into this category, but none that we're going to be working with. Now, the takeaway for this is going to be a slightly different arrangement of ligands, right? So, for example, if we were looking at the addition of ammonia to copper, then even though we're aiming to get to coordination number 6, the distorted octahedron that forms is going to maintain 2 waters, right? So here what we're doing is substituting waters for the new ligand. So in the case of copper, we don't actually substitute all the waters. Again, this is in large part because of the energies. So what we end up with is still an octahedron, but we keep 2 waters and substitute 4 ammonias. Now, that means, so for when you're coming up with a formula for copper complexes, you want to keep that in mind, right? So again, the 2 rules that I just said, chloride is tetrahedral, everything else is octahedral. The only exception being that with copper, in octahedral geometry, it's going to have this dual arrangement, the new ligand and water, and it will always keep the 2 waters. That's the generalization we're keeping here. There's a question. So the potential energy is of the complex, right? The complex itself has an energy, and depending on what we do to it, it can either go up or go down in energy, right? Going up in energy is not favorable because that's less stable. But the potential energy going down is a stabilizing factor. And stronger ligands have better ability to lower potential energy. Yes, so with copper complexes in part B, you'll always maintain 2 waters and substitute 4 of them, right? Just like here. This is starting out as aqueous copper, which has 6. We substitute 4 and maintain 2. So with respect to, so in general, for everything else, the order doesn't matter because it's only one ligand. For the sake of copper, for our purposes, the order doesn't matter. The order would, yeah, so whether I put ammonia first or water first, it's the same difference for us. There's no real difference there. All right, so I am going to, let me just skip ahead. At this point, we're already over, so I will come back and talk about malachite in the beginning of lab this week. But I do want to skip ahead and just finish with the safety and some announcements. In terms of the safety, pretty standard. The two specifics would be making sure to work under the canopy hood. In the Barron experiment, because the ligands we're working with are concentrated and some of them do fume. Also organization, because there are lots of trials, meaning all of the different reactions we're going to look at. So organization is important so we don't, mix things up in a way that could potentially have a side reaction. Now, in terms of, I sent out an announcement about this last week and also a reminder last night. This week, we are starting with the at-home kit. Now, just be aware, the way lab will work basically for most of the rest of the summer is it's going to be in two parts. We will continue in the same paradigm as we have, meaning we will start class with the online experiment. Somewhere towards the end of class, we will reconvene and then talk about the at-home experiment. So for the next bunch of weeks, we'll be doing two things during lab: online experiment and then an actual at-home experiment. They are not the same thing. They're going to be completely separate items. Now, our first experiment, basically the at-home experiments are going to fill in and also look at some of the techniques that we did in the first half. So our first experiment is going to go back all the way to experiment 1, and we're going to now determine at home the density of water, right? So we will be able to actually do that experiment at home using the kit. So the items that you need are here. Also make sure you have something in case of a spill. We're only using water, but just in case of a spill, it's a good idea to have some kind of towel or, cloth in case you have drips. Data collection must be done during lab with your TA supervision. So the at-home experiments can only be done with us live. And again, all of the specifics of that are in the announcement. So important to review that carefully. Now, the at-home experiments do not have a pre-lab. There will be a report sheet for most of them. The report sheet will become available basically during class. I will talk about the experiment and demo it, and then you will actually complete the experiment with your TA. Again, this week, since it's the first one, we will go through all of that, and I'll explain this again when we're actually live during lab throughout the week. Now, most of the at-home experiments will have some calculations. They are not very long. They're only maybe 1 or 2. And it's best to complete those before you leave. They're not due at the end of lab. I'll explain the deadline throughout the week. But it is best to complete those before you leave so you can be done with that and get any help that you need. And then lastly, again, since now we are going to be doing the at-home portion of the course, make sure to review the dress code in the announcement, because that is something that we will be checking for in lab each week. All right, now just to close with some announcements. So quiz 5 will be released later today. As I said yesterday in the announcement, the practice exam will be released tonight. Now, similarly to report 5, report 6, you also have 2 weeks to complete. So this is due in 2 weeks. I would recommend do not wait until the last minute with this, because this topic is new to many students. So I would try to start working on this sooner rather than later. It is a pretty standard report, pre-lab on lab archives, the post-lab items, calculations in the notes, and then there are 2 report sheets. Now, be aware, the Barron report sheet has a lot of data analysis. There's a lot of qualitative data analysis in Barron. There are no calculations in the Barron portion. The calculations are only for the malachite. But the Barron report sheet is a bit involved. Now, next week, we have another holiday on July 5. That's in observance of July 4th. So there is no class, no office hours next Monday. I will send out an announcement later in the week reminding everybody. But next week, we will be entirely off Monday, July 5. Next week, there is no lab, as is stated in the syllabus, because the midterm will be next week. And I did send out all the details about that last night, so please take a look at that announcement for that information. Now, I will also be in touch with a reminder in terms of how office hours will work. Monday, July 5, there will not be office hours. The rest of the week, office hours will be as normal. The other thing is that I will most likely do an extra office hour in advance of the midterm. That way, if there are questions right before that, I'll be available. There's a question. The Excel activity is listed to be due on July 12th, but I am going to postpone that a week. Given that the midterm is next week, I want you to focus on that. So I will send out an announcement with that update, but the Excel activity is going to be due a week extra. So it'll be due on the 19th instead of the 12th of July, but I'll clarify that in an announcement. All right, so I will finish there. Actually, I'll finish with this slide because it's some pretty pictures. And see, this is actually about malachite, which we'll talk about in lab. But I will stop there and see what questions do you have?
Do you have a rough idea of what materials we'll be using from the lab kit this week?
Well, I know exactly what materials you'll need, and it's in the announcement.
Okay.
So the announcement gives you exactly what we're doing and exactly what you need.
So Professor, I want to confirm that you've said that in the email the midterm will be multiple choice, so it will be different with quizzes we've taken during the semester.
Yes, that's correct. So the format of the midterm is going to be different than the format of the quizzes, given the difference in the assessment type. But again, the practice exam will hopefully show you that formatting.
Okay, thank you.
Correct, sure. Yes, this week, so this week is entirely normal. There's lab throughout the week. Next week is different because of the July 4th holiday. So there basically is no class next week, but Monday, July 5 is a university holiday and the entire university is closed.
Sir, the midterm will be presented in the asynchronous format as well, correct?
That's correct. So the midterm will be presented pretty much in a similar way to the quiz. And again, all of those details are in the announcement that I sent out yesterday.
Gotcha.
Relative to the best way to prepare for the midterm, do you think it's to review all of the quizzes, or also, I'm assuming it's the quizzes and the experiments and the lectures, but how granular is it relative to what happened in each experiment?
So I think I think the best answer to that is once you look at the practice exam, you'll have a much better sense of that. So the midterm is not going to be about procedural specifics. It's going to be they're going to be general questions about the topics that we covered. So the procedural sort of details are not overly important for the midterm. It's going to focus entirely on the concepts, whether they be qualitative or quantitative. So in terms of reviewing for the midterm, the practice exam is critical. There's the study problems, most of the quiz questions, the pre-lab questions in the manual, and then my lecture slides.
Thank you.
Sure. Sevilla?
Hi, Professor. So I just wanted to clarify for tomorrow, we're going to be doing that's my lab section, but in lab this week, we're doing the at-home experiment. And will we be going over experiment 6, or will it mainly just be one or the other?
It's going to be both.
Okay. Okay.
So we will start, and it'll be similar to what we've done. We'll start class with experiment 6. There'll be the breakout room for a while. We will eventually reconvene, and I'll explain the at-home experiment. And then we'll go back to the breakout room for a second time for you to actually complete the experiment.
Okay, perfect.
So
Thank you so much.
It's going to be 2 parts. Yeah, Emma.
Yeah, this is just a general question on the practice problem that you posted for this experiment, for experiment 5. I saw that you wrote something about like ignore this significant figure rule. And then I was looking at the specific ones where it was like pH and concentration. Is there like a general like pH is always going to be this number of sig figs or decimal places? Because I've seen like it varies between questions.
Well, yeah, that's because so there is not one set. It does depend on the question.
Okay, so should we be mirroring it as like when we say we started with the concentration of like H+ ions that we got from a strong acid or something? Do we mirror the sig fig and decimal points as what it is for that beginning thing, or does it just like how do I determine the pH one from that?
Well, so in the study problems, there are certain questions. I mean, I've tried to given the answers in the correct sig figs or decimal places based on the question, but for the sake of solving those problems, it's not an aspect I'm worried about.
Okay.
So, for it's 2 or 3 questions, I believe that it indicates, as long as you can solve the problem and get something close to the answer, that's the important detail.
Okay, that's what I saw at the top. I just wasn't sure what that meant regarding sig figs.
Yeah, I mean, basically for those types of questions, it's not all that important because I want you to understand the concept, not get bogged down in the sig figs.
Okay, perfect. Thank you.
All right, anyone else?